Hello, it's Keith here, and this is lesson 5 of the Photon series of my 68,000 assembly programming tutorials. Today we're going to be looking at the Sinclair QL, and we're going to be porting this little Tron clone to the Sinclair QL, and this basically means we have to do a PSET and a point routine to set and read pixels from the screen, because all of the graphics are done with just those two commands. So you can see we've got our title screen here and our Photon logo, and as I say, this is all done with pixel plotting. And if I start the game, we can have a look at the game. So we've basically got to catch up with our CPU controlled enemy, and we've got to make him to collide with our line, and if we manage that we win, and if we collide first we lose and are rather stupid for being beaten by such a basic CPU AI. But it does happen quite often to me just like that. Anyway, the game's pretty simple, but there are a few points I need to show you because we'll see them in the source code in a moment. Firstly, if I press a direction, I have to release it and press again to turn in the same direction, and that's so we don't collide into ourselves, because if we kept detecting without any kind of release, then we just go straight into ourselves like that. The other thing is there's a boost mode, and this is where if I hold down the space button on this system, usually fire, I will move faster until the boost counter, that's in the corner down there, goes to 0. And this is just basically so you can catch up with the CPU, and it gives you some challenge to try and catch up with the computer, and it also often means we go too fast and crash into things, which makes us feel silly. So lots of fun to be had there. Anyway, we'll see those in the source code, and basically this is a tutorial on pixel plotting and pixel reading from the screens on all of these different systems, and it's just a nice way of seeing a different kind of game rather than the bitmap games we did with YQuest and things like that. Let's get over to the source code and let's take a look at what we've got. Okay. So here's the game code, and we're going to go over it. Now the first thing we got here is the color mappings. Now on some systems we have a palette that's redefinable. On this system we don't have that. We only have a fixed palette of 8 colors, and these are sort of the primaries. So we're using cyan, magenta, green and yellow, and Photon is actually a fantastic game for the Sinclair QL because it really plays to the benefits of that limited color palette, because we only wanted to use those primaries anyway, and that's exactly what the QL's got. Also, it's not too taxing on the CPU, so it doesn't have the speed limitations that the Grime 68,000 had, for example. Now what we're doing next is we're defining the screen size here, and again Photon really can work with any screen size because it's pixel based. It draws a border around the screen, and the screen can be any size, any weird shape. It will just draw the border accordingly, and it will work just fine really. So that's what we're doing here. So we're using the full 256 by 256 range here. We need a few variables for our games, so we're just defining an address for those there. And then we're starting our program here, turning on the 8 color mode here, clearing the game memory, and we're showing the main menu, and that's in the multi-platform code. So that's just going to draw the title screen, wait for fire, and all of that kind of good stuff. Now here's the main loop. Now the boost mode works. Basically the game has 2 ticks. It goes between tick 0 and tick 1. If boost mode's on, we move every tick. If boost mode is off, we move every other tick, and that's how we slow the game down for when boost mode's off. So that's what we're doing there. Now we've got a loop here, it's a delay, and we read in from the controls, but the time we actually delay is lower if boost mode is on, and that's not to speed the game up, that's actually to compensate for the rather slow, crappy font drawing routines I wrote, which unfortunately aren't that fast, but they are very portable. So we're having to compensate. Basically when the boost count is going down, we have to delete the old count by drawing it in black, and then draw the new count in the colour. So yeah, as I say, it's a little bit slow, but it is portable. So we've got that speed to change there, and then what we're doing here is we're reading in the controls, and we're seeing if any keys are pressed, and if they're not, we're clearing what's known as the key timeout, and that's because we have to release a key and press again for it to be registered if we've already held down a key. And so that's what we're doing there. If any keys are pressed, we're storing them in D2, which is our key buffer here, and we just wait until the loop count reaches 0. Next, what we do is we see if that key timeout is still set, and if it is, we're going to skip all of these controls because the player needs to release first. What we do next is we're setting boost to off. Writing 1 to boost sets it to off, and that will disable boost. Boost will be enabled if the fire's held down. We're then setting A3 to the player's direction, and the acceleration of the player is A6, and this is because if the player is pressing left or right, we're going to decrease or increase the direction. It's going to be it's 90 degrees north, south, east, west type, and 0 to 3, and the set player direction function will transfer the correct accelerations into the register A6, which is pointing to the player's accelerations here. So that's why we're doing that there, and this does all the work of setting the new direction, and then we just set the key timeout to on here if the player's pressed one of those directions, and that will stop them from crashing into themselves with any luck. Then what we're doing here is we're checking the fire button. fire button's pressed, we check if boost power is 0, and if it's not, we turn on boost by clearing the boost count register here. You can see we were turning it off there, we're turning it on here, and that will turn on boost power. Now the actual boosting is done by the handle player routine, and also the collision detection, the drawing, all of that kind of good stuff, and the handle CPU does the CPU style stuff. Now you should notice, of course, key timeout was never set for the fire button because you need to be able to hold down fire to keep moving faster. So fire is accepted from that limitation. Now the other thing that's worth noting here is this is the entire code, the infinite loop here, that's the main game loop. It's very small and that's what we want. All the dirty work is in the multi-platform code, which is where we want it, so we don't have to keep rewriting it every time we port to a new system. I certainly don't want to do that, even if you do. So there we go. Now that's the basics of how the game loop works, but now we need to actually look at the colors. Now the screen on the Sinclair QL is a little bit unusual. Basically, there are 4 pixels in a block, and we have 4 possible bits for each pixel. Now there is a green bit, a flashing bit, a blue bit, and a red bit, and these are basically split into 2 bytes. So in the first byte, we will have the green bit and then the flashing bit for the first pixel, then the green bit and the flashing bit for the second pixel, you can see them here, and then the green bit and the flashing bit for the third pixel, and then the green bit and the flashing bit for the fourth pixel. Now the following byte has the same 4 pixels, but this time it's the blue bits and the red bits. So basically we need to set all of these bits for our color. We're not going to use flashing, but we need to set these according to the color we want, and we're going to use some pixel masks so that we can actually sort of target the pixel we want to change. So you can see we've got these masks here for the bit that relates to each individual color. So this is pointing to the first color of the first pixel in the byte. This 2 bits along is the second, this 2 bits along is the third, and this 2 bits along is the fourth. And we're basically going to use these for the first byte to set the green pixel, then use them in the second byte to set the red pixel, and then shift them once, and then we will be able to set the blue pixel as well. So we're going to have to use these multiple times to set our color. So here's our function, our PSET routine. It's going to take an X and a Y coordinate in D1 and D4. It's going to take a color in D2. And these are going to be a pixel position, and what we're going to do is we're going to use the get screen position function we looked at before in the simple series, and this takes a byte coordinate, or used to rather, and so we're going to convert it. And so what we're doing here is we're shifting to the right by 2 bits, and that is converting the pixel X coordinate into a byte X coordinate. And then we are basically multiplying that by 2 to get the word position, and that's calculating the X offset within the memory, and then we're taking the Y position and we're multiplying by 128. And the reason for that is it's a 256 pixel wide screen, and it's using 2 bytes for every 4 pixels, so effectively we're getting 2 pixels per byte in total. So that's why we're doing that. We're doing those shifts there. We're adding to the screen base a hexadecimal 20,000 here, and that is calculating the memory address that contains our pixel. Now, of course, we need more than that. We also need some masks to work with that pixel, and that's what these are doing here. So we're then calculating the offset within the pixel lookup for the pixel we want to change. So we're then getting the mask, and that's a typo there, it should be okay. So we're then getting the mask for the pixel that we want to change here. We're loading that into D1, flipping the bits, and that is now the mask for the pixels we want to keep. We don't want to change at this time, and then we're loading the mask for the pixels we want to change into D3. So we've now got 2 masks that we can use to tweak each bit if plane effectively of the pixel we want to change. So what we're doing here now is we're loading in the current screen byte. We're masking the pixels, the bits that we don't want to change, so we're effectively zeroing the pixel we want to change, the color of the pixel we want to change. We're then taking a bit off D2, the color we want to set it to. If that's a 1, then we're ORing in the mask for the bit of the pixel we want to change, and that's effectively setting that bit plane of that pixel to 1, and that will set that color. We then store the new byte back to the screen, either with that pixel set or clear, just that bit set or clear, depending on the color we wanted to set. We're then adding 1 to our memory position in video memory, and that's moving on to the second byte, which will contain the red and the blue. So what we're doing then is we're doing exactly the same thing, reading a byte from the screen, masking to keep the background pixels. We're then taking another bit from our color, and if that is a 1, then we're setting it, and then we're storing that back. And so now we need to deal with the final bit, the blue bits. And so what we're doing here is we're shifting our masks to the right by 1 bit, and that will now look at the extra bit of the pixel, because remember the two colors are neighboring each other within the bytes. And then we are basically using our masks again, testing the last bit of our color, because it's going to be 0 to 7, and we're setting the pixel accordingly here. And so that's setting our color of our pixel to the one we want via these 3 bit plane alterations here. Our point routine is basically the same. We're just reading in from the video memory here. We're using our masks here. This time we're only using the mask for the pixel bit we want to look at here. We're then testing each of those bits, and we're setting the bit planes accordingly, setting 1, 2 and 4 here into the destination value here, which is the pixel we've read from the screen, and this will set the value according to the color on the screen. Now it's worth pointing out that Photon doesn't really care about the color, it only cares about if the pixel's 0 or non-zero, but basically that's actually working out the original color just for completeness. But as I say, we don't really need to go that far, and that's how we read in the pixels from the screen for our collision detection. We've also got a clear screen routine here. We're just taking the screen base, calculating the size of the screen in bytes here, 256 lines, 128 bytes per line, and using this clear routine here, which will clear the bank of memory for us. And then the rest of the code is stuff we've actually used before. This was all covered in the simple series. If you want to know how to read joysticks, please see the simple series of joystick reading, and that's all covered there. So there we go. The Sinclair QL screen is a bit of an odd layout with this alternating pixel colors here, but it's not too bad to work with. So yeah, once we get used to it, we can pretty easily work with it and make it work the way we need for our pixel plotting. Anyway, if you've liked what you've seen today, you can get the source code from my website as always, and you can hopefully have some fun with it and maybe you can make some use of it. And if you do, the best of luck to you. If you've liked this video, please hit the like button. YouTube recommends videos on likes, so that would help me out. And if you subscribe, then you'll probably see when some more Sinclair QL tutorials come along, because I'm sure there will be some sooner or later. Anyway, I hope you've enjoyed this today. Thanks for watching. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers, so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all 3 are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.